All right, so another really popular topic in the science of infectious disease right now, and in the popular literature, are what are so-called gain of function experiments. And so this has come up several times in several questions in the forum. And so this is research that adds functionality and in fact oftentimes increases virulence of existing pathogens to allow us to study them and study the characteristics they have when they're now worse off, right? But so many of us can immediately, from a sort of sci-fi standpoint, imagine what the costs and the fears associated with these experiments are. But so the important question is, what are the potential benefits are there for these? And if there aren't any, then perhaps we shouldn't be doing them. But we need to understand what the potential benefits are if we're going to have a reasoned discussion about whether or not these experiments should continue.
So maybe not everybody have heard about it. I think there's been a lot of discussion about it, but I think one of the big issues that precipitated this discussion was it 2 years ago when there were two different labs that genetically engineered the H5N1 influenza virus, the highly pathogenic virus that killed most of the humans that were infected, but never transmitted from human to humans. And then they engineered these viruses that they showed in ferrets could transmit from ferrets to ferrets, which is oftentimes a good model for transmission among humans. And those, I think there were two scientific studies that were embargoed for 6 months or so because from being published, because nobody knew the risks associated with this. And so that's just a clarification of an example of what we mean by the gain of function.
I think that example is really important because we as a scientific community don't know what we're doing, so it's really important to, it's true, I know. There was recently the formation of the Cambridge Working Group. Marcel Salaté is part of that, and they gathered together a whole range of scientists to figure out what might we do, because we really don't know whether labs should work on this and how, to what extent government authorities should step in and mandate that this work shouldn't be done, because it is absolutely clear that it's very dangerous work.
So there are clearly uncertainties, but what are the potential? Why do this in the first place?
There's a long history, and the rationale's pretty simple. If you can identify a specific part, or say a gene in an organism that is responsible for disease, then you actually have a target that you can aim for therapeutics. Okay, and so the classical experiments, and this goes way back, is as long as we've had molecular biology or could do inbreeding of some sort, is to just take a genome and swap genes in one at a time and see which ones give you the phenotype of disease. And that's how we identified a lot of these virulence factors. And that's what's led to a lot of the therapeutics. And so, that's sort of the background in which these can be beneficial. The transmission experiments get you into another realm because they're really changing the biology of the virus of an organism. In one case, you're just asking, we know we have a bug that can cause a specific disease. What part of it causes that disease? In this case, we're trying to confer a new phenotype.
So my take on it was perhaps slightly different, and or maybe not. In that those experiments were really asking the question, is it possible for this virus, which occurs in nature, to actually become one that transmits between individuals? Nature does these experiments on a routine basis, on a daily basis, 1,000 times a day probably within us. And so in essence, what these scientists, those two groups, were asking was, can you do that? Or is it even practically possible for this virus to evolve to that state? That's really important information to have. And without that information, we won't be preparing appropriately for that. The embargo was actually motivated more from a sense of, can you provide this information now to certain bad actors who will then engineer this virus to do things that it shouldn't be doing. And so those experiments were already done. They were approved experiments. People went through, but done in very safe settings with very highly reputed groups. So there was really nothing wrong with the experiments themselves. It was really how the knowledge would be used by bad actors.
Yeah, but it's gone beyond that now, because I think you're a signatory of the Cambridge.
So I signed the Cambridge Working Group document after some thought. I do feel we have to be very cautious when you start to say scientists shouldn't do things, because that way is a very slippery slope. Cambridge Work Group is actually saying there should be a moratorium on it, and while we figure out what's going on, like there was for recombinant DNA in the 70s. And it's only on some pathogens, so SARS and MERS and a few of the flu strains. To me, I think that the sort of question you're talking about is what evolution can do, what could come up. You have to ask yourself, do you need to do this on a virus which is horrendously risky for humans? So if you're asking general principles, and that's what's the great thing about so much of this DNA technology, we can ask questions of a whole range of things that either aren't for us or they're not that nasty. We're talking here about particularly nasty things, that if they got loose, catastrophe could be visited on us. So you have to ask, why was it necessary to do those experiments in those particular pathogens? What are we getting out of studying those? And the justification there has been, well, it's something to do with surveillance, not therapeutics development, surveillance, that 5 mutations to mammalian transmissibility was the sort of answer they were giving, and it's these 5 mutations. So you've got to keep an eye out for those, and if you see 3 of them in nature, we're really close to a disaster. That's the sort of logic. And to me, as an evolutionary biologist, I think, well, that's one pathway to mammalian transmissibility, but in ferrets, but there's going to be many other pathways.
That's right.
So the predictive power of identifying a few mutations strikes me as being very low. We don't know. I mean, that might be the only route. It might be predicted, but we don't know that. I'd like to see that in other systems, safer systems first. How good is it as a way of developing surveillance systems to generate horrendous viruses and then go looking for elements of those in nature? To me, that's a completely uncertain. And so given that we don't know if that works, and the risk if these things get out, and we know very many labs that have released pathogens we didn't want to lose, that's why I signed the thing in the end. It seemed to me very, very uncertain gains.
Sorry, yeah, so totally concur with that rationale. It makes perfect sense. The virtue of, but perhaps the value of getting that information is that we now know for a fact that there is a path in ferrets that will lead to that. Not having done or not having access to the natural experiment, which actually would be devastating should that occur, we would not be able to ever know that information. So in this way, we're at least able to know for a fact that this is possible.
Yeah, I do take
and
that.
if it is possible, then we need to be watching out for it.
I do take that point, and I think actually Otto and I were over cocktails on the weekend discussing this very issue. And I think, well, Otto, not to put words in his mouth, was arguing that we did learn some interesting biology from that process, and that might help us with risk evaluation.
Absolutely. So yes, and so I must say, I am completely undecided on this topic. I think I might be slightly convinced by your argument, but I do think that it's very interesting in the case of H5N1 that there were essentially 2 sets of things that needed to happen. One was that you needed to change the epitope affinity of the virus, and then the other thing was that you needed to change the temperature range of the polymerase. And I think and so maybe the trivial result was that you changed those 2 things and you got gain of function. But I do think that one of the interesting corollaries is that with the change of temperature affinity, that's what allowed the virus to replicate high up in the respiratory tract of mammals instead of deep down in the lungs where the temperature is the same as the gut of birds. But interesting biology is that then, at least potentially, you could see that a lot of the virulence is really associated with the replication very deep in the lungs. And so it might be that there's kind of a trade-off or conflict, that you can get transmissible viruses, but they're likely to be much less virulent just because the function of transmitting is associated with being up here in a low temperature, less pathogenic environment. So I do think there was some interesting biology.
Yeah. So the slippery slope then becomes, every experiment you do on influenza has the potential to actually go down that same path, create something that has increased transmissibility, if that's what you're testing for. Many of those experiments actually don't test for that. So any experiment you do with any pathogen has the potential to make it more or less virulent. And we know from, for example, studies that have routinely introduced antimicrobial resistance into pathogens. Some of them are drugs for which if an organism such as TB becomes resistant now to 8 different drugs, there are no treatments for. How do you deal with that? And in fact, the importance of, I think, this sort of the sense of gain of function experiments onto specific paths means that you'd have to stop experimenting on pretty much anything.
Yes.
Because it's very difficult to predict what that gain of function might be.
I agree on that. There is obviously a very strong argument for gain of function experiments. I've got no issue with that. The question is whether we should do it where we're trying to enhance certain types of function, in this case mammalian transmissibility, in pathogens that we're genuinely very scared about. We have every reason to be very scared. And I think this discussion is an example of why we need a moratorium here. We need to pause to think, what sort of questions are we really going to get good things out of for taking these risks? And that has to be put up against the possibility these things get out. And you can measure the rate at which people lose pathogens. I mean, the pathogens get out of labs, and it's it's not zero.
Yeah. And this is clearly a discussion that's going to be continuing in the scientific community for some time to come. And I think I would really encourage more discussion about this. In fact, on the forums, to get some more perspective from the people that are taking this class in terms of what does the community that benefits from this science really get from the kinds of work that people like us are trying to do.